Continuing on physical chemistry, we're in chapter 19 now. We're doing section 3. Chapter 19 is more of a chapter 18. We're no longer talking about a particle in a box. Now, chapter 19, section 1, it just talked about units. And then chapter 19, section 2, it just gave a historical background. So now we're going to talk about the hydrogen atom. Now, ordinary hydrogen atom, of course, 1 electron, 1 proton, 0 neutrons. So we write it like this: hydrogen, 1 and 1. So this is a 2-particle system. So now we're going to talk about hydrogen-like atom, which would be really an ion. So it's anything with just 1 electron. So it'd be hydrogen, neutral atom, or helium plus, or lithium 2 plus, etc. So different nuclei, but just 1 electron. So it'll behave a lot like the neutral hydrogen atom, just we got more protons in the nucleus. So now let's talk about the potential, which is PE, potential energy, minus Z prime times E prime over R. So the minus, because it's got attractive potential, and then the E prime is the charge of an electron. It's going to be stat C or stat coulomb, because we're going to do Gaussian units. And then Z, E prime is the nuclear charge. Now we're going to be using CGS units for these calculations, because then we can avoid having to use any constants. So we get E prime is equal to 4.8 times 10 to the negative 10 ESU, which is electrostatic unit, or electrostatic units. And then E is going to be 1.60 times 10 to the negative 19 coulombs. That's the SI unit. So, and then C, of course, yeah, like I said, coulombs. Coulombs, however you say that. So again, we're going to have energy total is equal to energy translation, which is just like we did with the particle in the box, and then the E from the internal motion. So here's we got like a particle in a box bouncing around, etc., and then it's got 2 definite ends to it. So E tran is energy of translational energy of translation. So for hydrogen atoms, we use the Hamiltonian for the internal motion. So the Hamiltonian, H hat, is equal to minus H bar squared over 2 mu. Remember, mu is the reduced mass. Times the partial derivative, second derivative with respect to x, plus the partial derivative with respect to y, plus the partial derivative with respect to z, minus z e prime squared over r. So again, mu is reduced mass. And then the r radius is going to be x squared plus y squared plus z squared to the 1/2 power, square root. So basically the Pythagorean theorem. So again, mu is found by multiplying mass 1 times mass 2 divided by mass 1 plus mass 2. So mass 1 we'll say is the mass of the nucleus, and then mass 2 we can say is the mass of the electron, m subscript e. So mass of the nucleus will be 1,836 times the mass of the electron. So we have mu is equal to 1,836 me squared divided by 1,837. Remember, that's me plus 1,836 me. So we get 0.99946 me, which obviously we can just round and just say it's roughly the mass of the electron. So now we get the Hamiltonian times psi of energy times psi. Actually, there'll probably be Hamiltonian of psi time is equal to the energy times psi. So that's time independent. So here's a graph again. Remember, so we have x, y, and z in the rectangular coordinates. Then we have, so our nucleus would be out here and our electrons out here. And then the direct distance between them is the radius. And then we have this angle phi or phi, I think it's phi, which is on the xy plane. And then, of course, we have the angle theta between that and the z plane. And then converting back, we get x is equal to r sine theta plus cosine, or times cosine theta. Y is equal to r sine theta sine phi. I said that wrong, that'd be phi. And then z is just r cosine theta. So, but for x, the radius can be anything from 0 to infinity. And then for theta, it can be 0 to pi, but for phi, it can be 0 to 2 pi. So let's talk about the complete wave function for a hydrogen atom. So we have Psi is equal to radius, which is a function of these n and l, the quantum numbers, and then the r radius, times this symbol I can't remember what it's called, but it's also a function of these other two quantum numbers of theta, and then another function, I guess that'd be a capital phi. Yeah, this would be capital theta, capital phi, and that's dependent on the mass only of this other, the angle phi. So again, L, M, and N are quantum numbers. A0 is the Bohr radius, and then R of R is the function of radius. So we have, oops, I think that's supposed to be is that a Y? Yeah, that's a Y. So we have of L and M, so it's theta function based on L and M times phi, oh yeah, of theta, and then phi based on M of phi. So we say this is the spherical harmonics. The next is, so what is exactly the function, this radius? So we get R based on these two quantum numbers, N and L of R, is going to be equal to all this square root, N minus L minus 1 factorial, remember exclamation point means factorial, divided by 2n times n plus L factorial cubed. Notice the parentheses, all this cubed. That's the square root of that. Times 2 over n a0 to the L plus 3/2 power. Times R to the L power. Times e to the minus R over n a0 times this Laguerre function from n plus L to 2n plus 1, parentheses 2r over n a0. So this whole thing here, the Laguerre function from n plus L to 2n plus 1, that's the associated Laguerre function, and it's a polynomial of degree n minus L minus n. See a handout figure 72 and 80. So we have n is equal to 1, 2, 3, 4, etc., all the way to infinity. And we have L is equal to 0, 1, 2, 3, etc., all the way to n minus 1. That makes the function well behaved. So we have theta of theta is going to be equal to 2L plus 1 times L plus absolute value of m factorial over 4 pi L plus absolute value of m factorial. Take the square root of all that. And then here's another piece of L to the absolute value of m power of x. And then this is theta, remember. This is capital theta. So this here, this p of L to the m, that's the associated Legendre functions. So we get p is 0, 0, x is equal to 1. So we get p1, 0 of x is equal to x, which is cosine theta. And p1, 1 of x is equal to 1 minus x squared, square root of that, and that's equal to sine theta. So we get phi of phi is equal to a times e to the im phi, or phi, whatever you call it. Remember, phi is the angle, and then I is the imaginary number, square root of -1. So we have 2 pi, the square root, well, the minus square root of 2 pi, times e to the im phi. Now there are 3 variables for a hydrogen atom: the radius, the angle theta, and the angle phi. So that's why we have 3 quantum numbers, n, l, and m. So m can be 0, plus or minus 1, plus or minus 2, plus or minus 3, all the way to plus or minus l. So m of sub l is equal to minus l plus 1, blah, 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 all the way to l minus 1, all the way to l. That's another way to write it, because m is dependent on l. So if L is equal to 1, M could be -1, 0, or 1. Now let's, for a hydrogen-like atom with only 1 electron, remember, then we say that energy is equal to minus z squared over n squared times e prime squared over 2a. And then a, of course, would be h bar squared over mu e prime squared, which would be 0.5295 angstroms. So we say A0 is equal to 0.5292 angstroms. Oops, is that supposed to be a 2 or a 5? I'm not sure why that came out there. I'm going to underline that, see if I can figure that out later. Okay, so here we go. If we say that mu is equal to the mass of the electron approximation like we showed before, then use A0, rounded. Oh, I see. That's why. Okay, so if we use mu, then use A without rounding. So which one of these depends on if you're going to, approximate or use an exact number for the reduced mass. So remember, capital E is energy. E prime squared, like I said, that's E prime squared. And then M subscript E is the mass of the electron. And of course, A has dimension of length. So energy is proportional to minus 1 over n squared. So notice it doesn't depend on L or M. So we get degeneracy. So we have phi is proportional to N, L, and M. Now remember, degeneracy is the result of energy depending on N, but psi depending on N, L, and M. So we have different states that have the same energy. So here's an example. Start at the bottom of this graph. So for energy level 1, that's the 1s orbital, and that's psi of 1, 0, 0. And that's the orbital here. This is our wave function. So for energy level 2, we have the 2s orbital, which is psi 2, 0, 0, the 2p0 orbital, which is psi 2, 1, 0, the 2p1 orbital, which is psi 2, 1, plus 1, and the 2p minus 1 orbital, which is psi 2, 1, minus 1. So each of these 4 different wave functions has the same energy level. And then likewise for energy level 3, we have the 3s orbital, which is psi 3, 0, 0. We also have 3p0 orbital, which is psi 3, 1, 0. 3p1 orbital, which is psi 3, 1, 1. 3p minus 1 orbital, which is psi 3, 1, minus 1. 3d minus 2 orbital, which is 3, 2, minus 2. Psi 3, 2, minus 2. We have the 3d minus 1 orbital, which is psi 3, 2, minus 1. We have the 3d 0 orbital, which is psi 3, 2, 0. We have the 3d1 orbital, which is psi 3, 2, 1. And we have the 3d2 orbital, which is psi 3, 2, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. Of 9 different states all have the exact same energy level. Now, so for a hydrogen atom, like I just showed you, the 2s, the 2px, the 2py, and the 2pz have the same energy level. So we say that it's fourfold degenerate, because P0 is equal to Pz. Okay, so for a hydrogen atom, there is n squared degeneracy. Now remember, like I said, psi we're going to be representing in spherical coordinates, function of radius, angle theta, and angle phi. But r is the radial distribution function. Now, oh, okay, I've been pronouncing it wrong. Laguer here is pronounced Lagre. I think that's French. I never learned French. But Lagre, I'll try to remember that. So PE, potential energy, is also V, which is proportional to 1 over R. So the particle in the box, remember, had just one quantum number because it only had one variable. Lagre, darn it, different word. Legendre. Wow. Anyway, Legendre. For hydrogen or hydrogen-like atom, 1 electron, Schrödinger's equation can be solved exactly. So we get E is equal to minus Z squared over N squared times E prime squared over 2A. And we're using E prime because we're doing this in CGS units, that's all, so we can keep track of everything. Now the third energy level, we showed this on the previous graph, we're going to talk about it some more. So here they are, I'm not going to read it out loud again, I already read it out loud, but all those have the same energy since they have the same principal quantum number. But this is not necessarily true when you actually have 2 or more electrons. This is just for a 1 electron system so far. So let's substitute for A. So A is equal to h bar squared over mu E prime squared. And that, remember, the mass of electron is roughly equal to the reduced mass. So we have energy is equal to minus Z squared over N squared times E prime squared over 2A, which is minus Z squared over N squared times E prime to the 4th over h bar squared times the mass of the electron. So we get, put in the numbers here, we get energy is equal to minus Z squared over N squared times 2 times 3.14 squared, let's see, where was I? Times 4.80 times 10 to the negative 10 electrostatic units to the 4th power times 9.11 times 10 to the negative 28 grams divided by 6.626 times 10 to the negative 27 erg seconds squared. Now remember, conversion factor, 1 joule is equal to 10 to the 7 ergs. That's another unit of energy, obviously, if they're equal to each other. So E sub n is equal to minus z squared over n squared times 2.18 times 10 to the negative 11 erg, which is equal to minus 2.18 times 10 to the negative 18 joules times z squared over n squared. Or minus 13.6 electron volts times z squared over n squared. Electron volts is another unit of energy we already talked about. So here's a graph of energy in electron volts, but divided by the electron volts, so we end up with that units. And here's radius. So our ground state is way down here, and then the next one is n equals 2 is way up here, 3, etc., all the way to infinity. So notice how it goes asymptotic to infinity, towards infinity. But also notice, of course, it's not equal spacing. It gets closer and closer together. So V is dependent on R. The potential energy is dependent on the radius, obviously. So V is equal to minus E prime squared over R in CGS units. So V is equal to minus E prime squared over 4 pi E sub 0 R in SI units. So the negative sign, because remember the potential energy is attractive in this case. So negative potential energy means they're attracting each other. And then this, shoot, I forgot what that symbol is called. It's called the permittivity constant. And it's equal to 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. So at higher energy levels, the energy levels get closer together. Below zero energy, energy is quantized. Above zero energy, energy is continuous. Free electron can have any energy level. Okay, we're about halfway through section 3 now.